Test? Okay, perfect. Yeah, that's great. Thanks. Okay, well, good afternoon, everyone. Thank you for being here. So I'm Sebastian Crozet. So I have a background in physics simulation and linear algebra mostly. So you might know me from my Rust work on N algebra and Rapier for physics simulation. More recently, I started having some interest into GPU computing and in general GPU computing for scientific computing. And so I had interest into using the GPU for physics, linear algebra, and of course LLM Inference. So when I started this journey, I really wanted two key elements for working with the GPU. The first one is that I didn't want to have to write many shaders for different platforms. So I really want to work with a single source. So if I write one operator, I wanted to write it once and have it work everywhere. And this is kind of in line with how things work in Rust. In Rust, you write your code once, and you can be fairly certain it will work quite well on every platform. So that's the first item. The second item is modularity. Again, in Rust, we have a very nice package manager, which allows you to combine code from different projects. So I kind of wanted to have that for the GPU as well. So if I want to have a matrix multiplication implementation on one library, I want to be able to reuse that from a different library. If I have a quaternion implementation for the GPU on one library, I want to be able to import these shaders into my own shaders, which might be a graphics engine or even maybe physics or whatever. So the two key elements here are modularity and single source. And I think here I got a little bit lucky because towards the end of 2024, what happened is that Khronos announced that they would take over the Slang initiative. So at first it was a project developed by NVIDIA for quite a few years, so it does have some usage in production, but then it got donated to Khronos at the end of last year. And started this point, it became quite a bit more popular. So if you don't know what Slang is both a shading language and a shader compiler. So you will give it a Slang shader as input. You can also use HLSL or GLSL, but that's mostly for compatibility with existing code bases. But new code would be written in Slang. So you have your Slang shader, you use it as an input to your Slang compiler, and the output would be a shader for your particular target. So if you are targeting, I don't know, metal on macOS, it will generate an MSL shader. If you are targeting the web, it will generate a WGSL shader. It can target CUDA. Well, it can target everything on the right here. So you can see it has a huge coverage on potential targets, which is exactly what I was looking for, because I just need to write my code once, it will work everywhere. It doesn't mean it will work with the highest performance, you might hope, but it does gives you all the tools to go one step further. So for example, if you're targeting CUDA, you can write your shader in Slang for some of the operations, but you can still use QBLAS, for example, for some of the other operations, because behind the hood, it's still like regular CUDA. It's not like any kind of custom runtime or whatever. So you have a very good way to progressively write your shader and maybe improve it incrementally to get the best performances on the platforms you want to have specific code paths for. So this is only the shader part. So this doesn't tell you how you actually use that from a Rust code base. first, let me tell you a bit more about something I thought when I started with Slang, which is that, okay, you might know already this meme from XKCD, which is that, okay, we have a lot of shading languages, so we need to unify, we need to make something universal, so we do that, and in the end, we just created one additional shading language. And maybe it can feel a little bit like that, but in my opinion, it's a little bit different because Slang is still leveraging all this existing shading language, so it will translate towards this. And if today you want a solution for single source GPU computing, it's kind of the best option you have, in my opinion. So it's open source, open governance, again, single source for every platform. It will support both compute and rendering, which is important for me because I'm looking for GPU scientific computing globally, so not just LLM Inference. So I do want to create tools, to create shaders that you will then reuse for LLMs, but for physics, for rendering, etc. It's also a bit different from WebGPU, and actually WebGPU is one of the target of Slang, which is that WebGPU tends to be to align with the lowest kind of capabilities you have across all the possible targets. Slang is kind of the opposite, which is that it does give you the tools for all the targets, and if you try to compile toward a target which does not support a particular feature, you will just get a compilation error. But you can have like special cases depending on what your target can use. Slang also has an automatic differentiation feature built in. I haven't tried that yet, but I'm hoping that eventually it will allow me to very easily make a differentiable physics engine. It has a modern syntax, very nice language feature. It kind of feels like a mix between Rust and C++ to me. And if you are familiar with shading languages like WGSL, you know that modern syntax in a shading language is a very rare thing. It offers reflection, which is very important for as a developer, because one of the biggest difficulty when working with multiple shaders contributing to the same compute kernel is, for example, having to deal with binding groups. If you are familiar with rendering shader API, you will know that when you have to define your shader inputs, you have to assign a binding group and a binding index to each of your buffers. And if you start to compose multiple shaders that way, it's a huge nightmare to know exactly which index you want to set to avoid overlaps, etc., etc. So it's kind of a registry allocation task, which shouldn't be done by a human. And Slang can do this automatically for you, and you can use the reflection API to directly get, okay, for this argument, I need to use this binding group and this binding index. All right, I have this QR code here. So this is a talk which I think was published a few days ago. And it will give you some very, very complete information on what Slang does, future roadmap from Slang, and a few use cases. So this is some of the Kronos team during SIGGRAPH 2025, and I think it's very, it's a very good talk to get familiar with Slang. All right, so using Slang with Rust. How do you do that? First, you need a shader compilers, which is, of course, Slang. So that will take your Slang shader and create your platform-specific shader. This is C++. So you need to use that from Rust, so you need some kind of bindings. And these bindings here is the shader Slang library. So I was, again, a little bit lucky here because the Rust community already had that crate, and it does support everything you need for compilation, and it also supports the Slang reflection API. But now everything in green below did not exist. So that's things that needed to be created. Mini Slang is just a small wrapper around shader Slang so that with a few lines of code you can check compilation of your Slang shader at compile time. So when you type cargo build, it will also check that your Slang shader work, actually compile at least. And then you have an RHI, which is a render hardware interface. So that one, Slang HAL, is responsible for converting your CPU function into whatever API call is relevant for your platform. So for example, you rewrite create buffer to create a GPU buffer, but then for creating a buffer, it's not the same API for Metal or for CUDA, etc. So that's what Slang HAL does. And same thing for dispatching a kernel. You will say, okay, launch this kernel with these inputs, and then Slang HAL will automatically use correct API depending on the backend you want to use. And finally, and that's, I guess, the most interesting part, are the actual mathematical shaders. So we have a bunch of new libraries. So all of this, I started working on that only three months ago, so it's still very much work in progress. So you have S-tensor, so Slang tensor, which defines tensors in Slang. It defines matrix multiplication. It will define also operations between two tensors, like addition, subtraction, all the basic stuffs. It will also define some geometric operations on low dimensional entities, so isometry, similarities, quaternions, singular value decompositions, etc. So if you know a little bit about algebra, so the Rust library, it's kind of the same, but on the GPU. Nexus, that one is almost empty right now. It just contains some geometric operations, but eventually it will be a GPU-based physics engine. Slush, that one is also a physics engine, but for non-rigid objects. And finally, Sleigh is the LLM Inference library. So Sleigh would mean Slang AI. So let's have a look at some things from Sleigh. So I don't have any more slides for Slides, but I did want to show you a few elements from the Sleigh code base, so you can have a look, have a feel of how things work with Slang and some of the features. So it's still very early, in an early development stage, so it implements two models right now, which is HANGZHOU and segment anything one. And it might not have all the operators you want for your own model. But one thing very interesting with Slang is that if something is missing, you can implement the Slang shader and it will work on all the platforms. You don't have to implement 10 shaders for every single backend. You just have to implement one and that's it. So let me close this and okay. All right. Okay, so a few things I wanted to show about Slang AI. So if you were to try to use it right now, the main struct you would be interested in will be LLM context, because that struct contains every single tensor operations you might want. So this is heavily inspired by DGML. So one of my objectives was to make sure that we have like the typical DGML operations, and also it has some things which helps you transfer code from DGML to Sleigh. So for example, I can show this one. So it has a matrix multiplication, which is called matmul DGML, which converts like when you write matmul DGML AB, it's not actually computing A times B, it's computing B transpose time A, because DGML has a slightly different convention here for matrix multiplication. So there are a few details like that which allows you that if you look at some DGML code and want to rewrite this in Sleigh, you will have some help to transfer between the different conventions. So, okay, so this is all the tensor operations you can use. You will see that some of these operations take an output tensor, and some of these will return a new tensor. And what happens here is that Sleigh has an automatic tensor cache feature, which means that you don't have to worry about tensor allocation for intermediate values. It will all be automatically recycled when tensors get dropped. Okay, so that's the first thing, which is all the tensor operations. Then I wanted to show you some neat feature with Slang. So if I take, okay, I have all my Slang tensors, my Slang shaders here. If I just take one, it doesn't really matter which one. Yeah, maybe yeah, okay. So if I take softmax here, first thing you can see that it's quite a modern language because it might feel very natural, but even your kernel definition can take your buffer inputs like as arguments, and it's actually something quite unique. Like in most shading language for rendering, these would be globals, which is just terrible. But anyway, what I wanted to show here is this line, which is like the second point I mentioned at the beginning of this presentation, which is that I want to be able to reuse shaders from one project to another. Because most of the time what you will see is that you either have one huge shader which contains all your code for your particular platform, or you will have multiple shaders but still all part of the same code base. So what's happening here is that I'm importing the shape module from the linear algebra submodule from the stensor library. And import is a feature from Slang, and Slang has the ability to work with multiple collections of shaders. So you can configure include paths so that Slang knows where to look for your shaders. Now the problem here is that I really don't like include paths because it's very difficult to work with, and if I'm working with Rust, if I have a dependency which is hosted in crates.io, Cargo will download this dependency locally and move it somewhere in the .cargo directory, which is not trivial to really know the location. So what Slang HAL has is a way to completely hide this process. So if I go into my stensor library, which is a completely different repository and also a different crate, you can see here that I do have my Slang shader, which is shape, which is part of the linear module, which is also part of the stensor root module. So the shape here is a description of a tensor shape, and it's very similar to DGML because it supports up to 4-dimensional tensors, and you have the strides here. So that file is basically used by every single shader of Sleigh. So it's a module named shape. So we are in the stensor library, and you can see in the lib.rs file that we have these lines. So what this does is that it will embed all your shaders into the compiled executable. So it's very simple, like to share. Well, this one is a library, but at the end, when you build your executable, it will be embedded in the executable. And you have that function, which, given a Slang compiler, will make the compiler aware of all of these shaders. So with just these few lines, I can do something very similar in Sleigh, which is here. And all I have to do is call register shaders, the register shaders function from stensor, and immediately every single shader that was defined in my different repository and my dependency become available to my shaders in Sleigh. So that solves this issue where I really need modularity. Now, if you go watch the Chronos presentation from SIGGRAPH, they do mention that they have this long-term goal of having a package manager for Slang. And I do hope this happens some days. But in the meantime, in a way, you are using Cargo as your way to manage your Slang shaders here. One last element I wanted to show is that on the one hand, you have your Slang files, and on the other hand, you have your Rust code. So how do you kind of bridge the two? So the way it works is if I take softmax, I can go here. I think it's here. Okay. So I have a definition of the softmax structure, which contains a GPU function which has the same name as the Slang kernel. And here I have a special procedural macro which makes a link between the Slang shader and the Rust code. So this one will automatically create all the boilerplate you need for compiling your Slang shader and instantiating the kernel that then you can launch. Okay, so that's a few features I wanted to show. So like I said, this implements two models. I can run it here. Oh, it doesn't want, oh, okay. Just have to wait. Let me cross one here. All right. Oh. So the UI is based on Dioxys. So the way it works, it has a GGOF parser. So I can click open GGOF. I can go select segment anything, for example. I can load. So right now I'm on battery here. All right, so I can select a picture. So one day in HANGZHOU. So after I select it, so you can ignore this part, like the prompt here is just useful for text-based chats, but here it's just an image. So by loading the image, it will run the encoding part of segment anything, and then I have the image here. I can click on the image, and when I click, I get the segmentation results. So that's one, and the second one would be HANGZHOU, which I need to run. Yeah. Here. Here, so it's, oh well, yeah, okay. I can use DeepSeek with the Quen variant. Yeah. All right, and you will get like your typical chat feature. So give me a chocolate cake recipe, you submit, and then it has like its reasoning first phase, and then the second phase will happen afterward. Okay, yeah, so the idea of Sleigh is right now to provide as many operators as you need for implementing models. I'm not trying to implement every single models out there because there is a new one like every 2 days now. But yeah, the goal is really to reach feature parity eventually with GGML, so that contributors can start creating their own models. So if I just go back quickly to the slides, the last question here is what's next? Yep. Okay. Oh, yeah. Okay, I won't go to full screen because it's just laggy. So what's next? Basically everything. Like I said, it's very early days. So what needs to be done is complete the implementation of Slang HAL, implement more operators. I will drive this work mostly, like my very next step would be to implement a Whisper model to make sure that I have more and more operators that you might want. I do have this long-term goal of implementing the differentiable physics system so we can have more tools for physical AI and embodied AI. And in general performance improvements, because right now it's still behind Llama CPP in terms of performances, but it does get quite close to the Onyx Web runtime performances. All right. Yeah, thank you everyone.